Alright, in this video we look at section 15.7, a spherical coordinates example. It's just a pretty straightforward example of spherical coordinates. You might recall from a formula that you've been told, um, in high school, or just something that you've just known, the volume of a sphere. You know the formula of this, but you might never have um, really thought about where it comes from. So the volume of a sphere we have memorized is 4/3 pi times the radius of that sphere cubed. Okay, in this video we're going to look at where this formula comes from. We can place that sphere, we can put a sphere of radius r, we could center that at 0, 0. So here is a sphere of radius r. Okay, if we'd like to find the volume of that sphere, okay, we could do a triple integral. Okay, we could integrate the function 1, we could integrate dv, and we could integrate over the domain D in three-dimensional space, and D, the domain, is the sphere. Okay, so this is a solid region that we were trying to integrate over. And because we are integrating the function 1, okay, we're thinking of the density of this sphere being the same density 1. So when we do a triple integral, that we have then tricked this triple integral in computing the volume of the solid region D. Okay? So what we need to do now is just describe this solid region, okay, in a particular coordinate system. Okay? If you decided that you wanted to go the rectangular coordinates route, rectangular coordinates, you're going to have a pretty gnarly integral on your hands that you would have to do a triple integral. Okay, we're integrating 1. You've decided to do dv, which is dz, dy, dx. Z would go from the bottom part of the sphere. This is a sphere of x squared plus y squared plus z squared equals to r squared. So you would have to go from the bottom part of the sphere, negative r squared, minus x squared, minus y squared, up to the positive part of the sphere. Right? This is what you're looking at if you want to stay with rectangular coordinates. Now, it might be easy to set this problem up, but it might be hard to evaluate. So now we look at what's going on in the z equals 0 plane. We'll find that x squared plus y squared is equal to r squared. So y would go from negative to square root of r squared minus x squared up to positive square root of r squared minus x squared, and then x would go from negative r to r. And that is the integral you're looking at if you want to do rectangular coordinates. But fortunately, there is an easier way. The volume of a sphere. Okay, we need to find the volume of the domain D, and we're going to do that with a triple integral. We're going to integrate 1 again, but instead of doing in rectangular coordinates, we're going to integrate in terms of d rho, d theta, d phi. We're going to integrate in terms of spherical coordinates. And to make sure that this quantity right here is equal to dv, we need to fix the units. We need to make sure that we have meters. We need this to be meters squared, but it can't be at the moment because each of these is in radians. And so we need rho squared sine of phi to be the fudge factor that fixes the volume element. So the rho squared sine of phi is the determinant of the Jacobian of the transformation, the spherical coordinates transformation. And now we need to simply fill in the limits of our region. This sphere of radius r is comprised of, this solid region is made up of spheres of increasing radii, and those radii go from rho is equal to 0 up to rho is equal to the radius of the sphere. that you're trying to find the volume of. So this is a solid sphere, so like a rubber ball, and that rubber ball is made up of solid, that solid sphere is made up of increasing radii. Okay. Now, remembering that theta is the angle that's measured in the xy plane, we can see here that theta goes from 0 to 2 pi. And then phi was the angle measured down from the z-axis, okay? And phi went from only 0 to pi. So that explains, that describes the whole region here. And when you were to, if you integrate this problem out, you do an iterated integral. Integrate with respect to rho, you'll get rho cubed over 3 sine of phi. And then we'll evaluate from rho is equal to 0 to rho is equal to capital R. So the first integral, we get rho cubed over 3 sine of phi. So if you've ever wondered in the formula where the 1/3 comes from, it's coming from integrating rho squared to get rho cubed over 3. This 3 is going to be the 4/3, is going to be the thirds, the third part of the problem, the 1/3 part. So now we continue on with the next integral, the d theta integral. So if we integrate from theta is equal to 0 to 2 pi, r cubed over 3 sine of phi, d theta. R cubed over 3 sine of phi is a constant, so it can come out in front of the integral, the d theta integral, and then we'll integrate with respect to theta, and then integrate from 0 to 2 pi. And that's where we get our 2 pi r cubed over 3. Okay, that's what this integral works out to be. And then we have finally the last integral. We need to integrate, oh sorry, I forgot the sine of phi. So now we need to integrate 2/3 pi r cubed sine of phi, and integrate from phi is equal to, integrate with respect to phi, d phi, and integrate from phi going from 0 to pi. Alright, we can see here that 2 pi over 3 is a constant, the radius cubed is a constant, but when we integrate sine of phi, that would be negative cosine of phi, evaluated from 0 to pi. When you plug in the pi's, because cosine of pi is -1, cosine of 0 is 1, -1 minus 1 would be the 2, and that's where the 4/3 pi r cubed comes from. Okay, so this is a pretty standard spherical coordinates. It makes your life easier, especially if the region that you're integrating over is some sort of spherical region. And we can see here that the limits of integration are all constants. Okay, so when you have a spherical region, okay, the limits of integration are going to be all constants. Okay, we'll see examples of videos where the example will have non-constants for the limits of integration. So ends this first spherical coordinates example.